yes, I'd like first of all to thank the organizers for having me talking here, and so that we could at last meet in person after so long, and it's really a pleasure. Yes, in this talk, the title of the talk is very specific, and it concerns ideas from a discrete Morse theory and ideas from persistence, which is a tool of topological data analysis. So it can be seen as a bridge between today's topic of this conference and tomorrow topic, which will be topological data analysis. However, even if the title is specific, I'll give a broader presentation, not only concerning this specific topic, because this is part of a long-going research of mine with the several collaborators, trying to put in connection discrete Morse theory with multi-parameter persistence. The reason is that I do not understand the multi-parameter persistence very well, and I always hope that discrete Morse theory helps me to understand better. So for that reason, the outline of the talk is that I'll briefly introduce persistence, and then I'll connect it with to discrete Morse theory using discrete gradients, and in particular persistence preserving discrete gradients. And of these gradients, what I'm really contrary probably to what we have seen, where the flows were very important, I'll be mainly interested just in critical cells and their value under the function. And because my studies in these years have led me to the conclusion that the critical cells capture many interesting aspects for persistence, and well, in terms of dynamics, they critical cells in connection to multi-parameter persistence, they detect the places where gradients are anti-aligned. And so that's the meaning that we should keep in mind in this talk about these critical cells. And going more towards persistence, they are critical cells gives us the values of the parameters for which that are essential to fiber persistence modules. I will explain what it means, and to compute the matching distance for persistence module. And also this will be something I'll explain. So let me start with giving a brief introduction to persistence. Maybe tomorrow there will be more. Persistence can be thought as a pipeline where one starts from data. Data is usually given like this, meaning we have a cell complex. In this talk, I will always take it to be a simplicial complex for simplicity. And there is a function defined on the simplices of the simplicial complex. And these are the data we want to analyze. And using the function, as Jonathan has shown us today, we can study the sublevel sets of this function that is the set given a value u. For example, if this is a function from sigma, the simplicial complex sigma to R, we can take u in R, a value u in R, and we can take those simplices for which the function takes a value not greater than u. This is the sublevel set. And And we can also take care that the function is chosen so that if u is smaller or equal than v, then sigma u is contained into sigma v, and it is a subcomplex of a sigma v. And so it is a nested family of spaces, and we can take, then we can apply the homology functor, and each of these subcomplexes becomes a vector space, because usually we work with coefficients in a field. And also for each inclusion that we have a linear map connecting those vector spaces. And so after applying homology here, we obtain this guy, which is the persistence module. And so we have translated the data from some geometric or topological information to some algebraic information. But now this is still maybe still complex to understand this persistence module, and therefore we want to find the invariance of it. And here there are two strategies that people has used in the years to obtain invariance for persistence modules. Some people approach a persistence modules from the point of view of commutative algebra and quiver representation theory, and from that they immediately have, thanks to a famous theorem by Gabriel, that it is possible to decompose the persistence module as a direct sum of submodules, all of the same shape. They are called the interval modules because their support is an interval, and inside that interval they are just the field with maps the identity, and outside that support they are trivial. And but people got something very similar using not commutative algebra, but using Morse theory. And so also using Morse theory for when the function takes values in R, one can see that one can associate to the module some intervals where the first left endpoint of the interval is called a birth of a topological feature, and the right hand point of the interval is called the death of a topological feature. So, and the intervals one gets with the discrete with the Morse theory are exactly the same. Pairing critical values of Morse theory are exactly the same intervals that one gets using commutative algebra. And so just to give you an idea, I have taken this simplicial complex here, and I have filtered it so that this is a u equals 0, this is a u equal 1, u equal 2, and u equal 3, and this is u equal 4. And from this, what are the bars of the barcode that one obtains? For example, if we apply H0, and so we only study the connected components, we see that we start with the 3 bars because we have 3 connected components. And but when we get here, for example, 2 of these connected components merge, so the bar stops, and the other 2 bars continue. And this when we get to u equal 2, we see that another bar, another connected component merged to the previous one, but also a new bar is being created by this new connected component, and so a new bar starts. And here we go on, nothing happens because connected components are not changing when we introduce a triangle. And then we go on, and this new bar that was born later dies here because it gets merged, and this bar continues until infinity forever. And so you see we have this set of intervals that represent the topology changes, in this case connected components, along the filtration. And this can be used, this type of representation of invariants can be used for several purposes, just to analyze the shape of your initial data, but there are also theorems that guarantee you that these bars give you information. If you have bars associated to a sampling of an underlying manifold, these bars give you information about the topology of the manifold, even if you have got them only from a sampling of the manifold. And in general, the longest bar is the more important the topological feature it represents. And the very short bars correspond to the tails of the shape of the data we are studying, or even to noise. And what is interesting is that if we perturb the initial data, then we get different barcodes possibly, but it is a theorem that these new barcodes that we obtain are also similar to the other ones from the non-perturbed data. And to decide if two barcodes are similar or are not similar, one needs to use a distance between barcodes. So first of all, I'd like to say again that the decomposition one obtains here is exactly, corresponds exactly to the barcodes one obtains here. And to compare barcodes, one can use distances. Probably when one works with modules, one prefers talking about interleaving distance, and thank you. And when one works with barcodes, one talks about bottleneck distance. But it turns out that in this setting where the functions takes values in R, they are equal. So there is no difference, and I later explain what the bottleneck distance is. But now I want to move to a setting where the function takes values in Rn, and this is interesting because sometimes we have multiple measurements on our data, and so we want to consider them not separately, one by one, but all together. And so the pipeline is very similar to the previous one. In this case, when n is greater than 1, one talks about multi-parameter persistence, because we have one persistence, n parameters in this case. So u, the parameter u, belongs to Rn, but we can still form sublevel sets, only that now we have a different, so the value of the function on a simplex is smaller or equal than u if it is so component by component in the usual linear order. And when we have a sublevel sets, then we can apply homology and obtain a persistence modules. And now we are at we have to choose, because one option is continue using commutative algebra. In that case, we'll try to decompose the persistence module into indecomposables, but this is not possible as in the case when n is equal to 1, because there is not only one type of indecomposables, not only intervals. Indeed, the theory tells us that these modules are of a wild representation type, so there are many infinite families of indecomposables, so we do not have only one type of invariant here. And however, if we can do this, we have a complete picture of the persistence module. The other option is not to use commutative algebra, try to still use Morse theory, but in order to do so, one way, and this is the way I'm using in this talk, is to slice the persistence module along the lines so that I can reduce it to a one parameter persistence module, and we can apply, and in that case, for each, when we fiber the persistence module, in this way, we get the barcodes, and we can try to understand those barcodes from the point of view of Morse theory. But now what we get when we have a fibered barcodes is not a complete invariant for the persistence module. It is a summary of it. So not so, there may be many persistence modules giving the same fibered barcode. And so but the good thing is that both of this approach gives something stable, so that again, if we perturb f a little bit, we get a different persistence module or a different fibered barcode, and but it is not so different quantitatively, so that the difference is small. And to measure this difference, we can either use again interleaving distance, or we can use the matching distance. And I'll focus my talk on this part of the picture, and which gives something less than the left part of the picture, so not complete, not good, not so much good at the distance is not doesn't discriminate so well as the interleaving distance, but it is more manageable, and still yields stability. So this is another picture. I'll go more in detail in the pipeline. So I start with the simplicial complex. I take a function with values in Rn on this simplicial complex. So in this case, for example, n is equal to 2. So for each simplex, I have two values. And I can form, and I can ask that the function is monotonic, so that the sublevel sets are subcomplexes nested into each other. One way to achieve this is the following, and this is what I'll use in the rest of the talk. One can start with the function defined only on the vertices, so only these values here. And then one can extend the function to the other simplices, only just taking the maximum component by component. So here the value is 2, 2, because on the first component, the maximum between 2 and 1 is 2. And the second component is also 2, because the maximum between 0 and 2 is 2. And one can do this for every simplex. And in this way, one is guaranteed to obtain a family that the lower level subsets are subcomplexes. And so one can take the filtration, which is shown here in this picture. And so now, as I said, from the filtered simplicial complex, I can apply homology. And so now I can show you an example of a persistence module where the field I'm using for homology is F, and the linear maps are represented as matrices. So as you see, it is not something that a human can manage easily, this object, unless one finds, especially if there are not, it is not only 3 by 3, if unless we find ways of summarizing it. So so I'm trying to show you that discrete Morse theory allows to summarize it a little bit. So first of all, I'm using the same notations as Thomas previously, so that for me a discrete gradient V is a partition of the simplices into two families. There are singletons that are called the critical cells, and there are double tones or pairs of simplices where the requirement is that each sigma, the first simplex, is a face of codimension 1 of the second simplex 2. And this gives us only a discrete vector field that we can call it a gradient if it is acyclic, so that if we follow the flow given by these vectors that as usual are represented by arrows from sigma to tau, we can't form closed cycles. And so on the left, we can see an example of a discrete gradient vector field. On the right, this is not a gradient vector field because we can form this closed cycle following the gradient. And the red circle denotes the critical cell. And so as mentioned earlier today, from this gradient vector field, we can construct a sequence of simplicial collapses so that the cell complex contains less cells. And for example, in this step, we can collapse this pair. And in this step, we can collapse these two pairs, and the resulting simplicial complex is contains less cells, and it contains only the critical cells. And each simplicial collapse gives an homotopy equivalence, and so because I'm interested in homology, this is good because the homology groups are going to be isomorphic. And the idea is that the critical values of these cells help us identifying the steps of the filtration where there is a change in the topology, in the homology. But actually, we are not interested, or at least I'm not interested so much in a homology, but rather in a persistent homology. So I want that not only the homology remains the same, but also the persistent homology and so the persistence module remain the same or up to isomorphism. So I needed to accept only discrete gradients that are compatible with the given function. And compatibility means that if I pair, if the gradient v pairs sigma and tau, the value of the function on sigma and tau needs to be the same. So, and this is represented in this picture, where I can, for example, pair this pair and get this arrow, because this is allowed, and also this two gives this pair, and these two can be paired to give this pair arrow, and these two give this arrow. And but of course I can only base this on the values. I could, because if I only look at the values, I could not get a gradient. If I only look for a gradient, it could be not compatible. So I need to do something that takes care of both. And but this only shows that if again that I can perform simplicial collapses, and the fact that the gradient is compatible guarantees that the persistence module I get is isomorphic from the persistence module of the cell complex I get is isomorphic to the persistence module of my initial simplicial complex filtration. Of the filtration of the simplicial complex. And so first of all, let me say that this is already convenient for computations, because, for example, if I want to compute the fibered barcode of initial simplicial complex sigma f, it is more convenient first reducing it using discrete Morse theory, and then computing the fibered barcode.
Yeah, I'm sorry.
There's a setup where she could actually but not exclude. Requires a USB connection. The shoe doesn't exclude.
Okay, if you want, I can go on without my...
No, just find a way.
But it was working.
On this one?
Yes, I can see the slides here.
Yes. So maybe we should put it right here. Right?
Professor, you mind if I ask a question? We're talking about the fiber barcode is obtained by taking single parameter filtrations from this multi-parameter filtration, right?
Yeah.
So is there a canonical way you're choosing the single parameter filtrations, or are we using the Morse method?
Yeah, we are using all the possible lines, straight lines with positive slope or increasing lines. And so there are infinitely many, and my aim is to show that you can just focus on finitely many of them. So in principle, you should compute all of them, or at least all the lines passing through to values of your initial simplicial complex, of the simplices of your initial simplicial complex, but you can just restrict to the number given by critical values. This is exactly the idea. So which one should I use now? I don't know. So what I wanted to say is that exactly, if you fiber the persistence module, restricting it to lines with increasing, with positive slope, so increasing lines in the space of parameters, and you can do two things. Either you recompute each time you have a new line, or and the computation means you are reducing a boundary matrix, and so you are repeating many computations because maybe two lines just needed the same reduction, or you reduce in advance using discrete Morse theory. You reduce to critical cells, and then you compute the barcodes for each lines. And the difference is shown in this diagram, where this is for a data set that was a sharp data set. I don't remember the number of simplices, but I can check if you're interested. This is the graph you obtain depending on the number of lines, only 4 lines, 9 lines, 100 lines. If you do not reduce the simplicial complex in advance, or and this is the graph you get if you first reduce the simplicial complex to the Morse complex and then compute the barcodes for each line. And this graph here, which is practically overlapping, shows that computing all the heavy computation is really choosing the line and reducing, not so much computing the Morse complex, because this is the full process. This is only the part of computing the barcodes. So in practice, computing the Morse complex is not doesn't add to the time in computations. And of course, these are seconds in this picture. And okay, so this is the idea, but still we do not know exactly how many, because if 4 lines are enough, we don't need to do anything. If 100 lines are needed to have a complete picture, then there is a difference. And so we want to understand how many lines, but first of all, we want to be able to so of course that graph was obtained because we are able to compute compatible discrete gradients. And because remember, we want to compute a discrete gradient that is compatible so that the persistence module remains isomorphic when we move from the initial simplicial complex to its Morse complex. And one algorithm that has been developed to this extent is the following. One starts again with the function given on the vertices and extends these values to all the other simplices. We also need that this function on the vertices is component-wise injective, so it is injective component by component. And we first linearize the value on the vertices, so that from a partial order on here, we get a linear order on the vertices, sorry, on the vertices here. And then here we also extend using this maximum rule. And so we can consider lower stars of vertices where the simplices in the star of a vertex has all the same value And this can be further partitioned based on the value given by pairs of values, and we can perform a homotopy expansion on each of these subsets. And this gives us the discrete gradient compatible with the initial function. The nice thing, we have never developed the code to parallelize this, but it can be parallelized because all these lower stars are disjoint and cover this simplicial complex. And what I'd like also to add that the gradient one gets is even perfect in the sense of persistence, at least for two-dimensional simplicial complexes or three-dimensional cubical complexes. What does it mean that it is persistence perfect? Well, perfect means that the number of critical cells of dimension k is exactly equal to the kth Betti number of the simplicial complex. This is for homology. For persistence homology, this means that there is a critical cell of index of dimension k exactly for each change, and it has a value with parameter u, exactly if at u there is a change in topology with the sublevel set filtration for homology of dimension k. So it is the generalization of perfectness of a Morse function for persistence. And so this means that this algorithm for two-dimensional simplicial complexes captures exactly where the persistent homology undergoes a change, and the same for three-dimensional cubical complexes. So we have an algorithm that at least, and this is not restricted to n equal 2, it works for any n. So not only two-parameter persistence, but any number of parameters persistence. So we have a way for, because of course the trivial gradient would be the one where all cells are critical and you do not reduce anything. So, but this tells us that we can reduce the most without changing persistence. So now, what do these critical cells detect? This picture aims to show that they detect places where if I have a function with two components, f1 and f2, the two gradients disagree in the sense that they are linearly dependent, but pointing in opposite directions, for example. And so I don't know if you can see it, but in this region outside here, the two gradients are exactly the same, whereas inside the region they are opposite, because here all the arrows are like this, and here all the arrows are like this. And if we run the algorithm on this data set, we can see that the critical cells are exactly those colored here. Cells of dimension 0 are colored yellow, one dimension is colored blue, and two dimension is colored red. So here color is just the dimension. So we get really the part of the picture where sorry, where the two, I don't know. Where to?
During the break, we had the same thing.
So let me show it in a real data set. In this data set, In this data set, taken from the data of the Hurricane Isabel, these are two slices, the left one and the right one of the data set, where the first, on the left, it's shown the gradient of the temperature, and on the right, the gradient of the pressure on a cubical grid. And below you can see the critical cells that have been for this pair temperature pressure, and they have been clustered, and now color encode the number of cells in a cluster. So for example, if we only consider clusters with at least 2000 cells, critical cells, you can see that we can simplify very much the visualization of the data, and the two gradients are anti-aligned exactly at the eye of the hurricane. So this idea can be used for visualization purposes, but we want to use it also for fibering persistence modules. So again, what it means, does it mean that we fiber a persistence module? We have, for example, a 2-parameter persistence module coming from a 2-parameter filtration. And now we fix a line L, and we restricted the persistence module to that line, and we computed the barcode along that line. In this picture, the orange line is chosen. It must be increasing with positive slope. And because otherwise, when we restrict it, we do not get a persistence module. In 1-parameter persistence module. Now we get it, we can compute the barcode, and we can do this for every increasing line. And so this is what the fibered barcode is a map from lines with positive slope to barcodes of the restriction of the persistence module to L. And only that if we have m values, different values for the simplices, we have m² lines to consider. And remember that the barcode computation in the worst case takes m³ time, even if the example previously shows that in practice it is linear. So take this m³ as a theoretical because in practice it is often linear. So now, instead of doing this for any pair of values of simplices, we wanted to summarize the simplicial complex, getting it's a Morse complex which contains less cells and therefore contains less values. So, for example, for this filtration, there are only 3 critical cells that are in the for the values of the parameters pictured in yellow. And so these, the yellow values of the parameter represent the critical values of our filtration. Now we can take the closure with respect to the least upper bound, and because this is needed because otherwise when we are here, we have the effect of whatever is happened here and whatever has happened here. So also this is an important location for persistence. And so in general, we consider the closure of the set of critical values of critical cells under least upper bound. And when we have this set, we can define an equivalence relation for lines. And we say that the 2 lines are equivalent if they are in the same reciprocal position to the set C bar. Being in the same reciprocal position in the plane means that two lines are equivalent if they leave the same points to the left and the same points to the right. So for example, L and L prime are equivalent because both have C2 to their left and C1, C3, and C4 to the right, but L second is not equivalent to L and L prime because it has C2 to its right. When we increase the number of parameters, we can still define this equivalence relation simply checking on which faces of the positive cone of a critical value the line intersects the boundary, in which face of this boundary of the positive cone. So for example, for C2, line L second hits it on this face, and line L and L prime hit the face of the positive cone on this face, and so L second is not equivalent to L and L prime. So this is a notion that can be carried on for any number of parameters. And so the idea is that these equivalence classes of lines with respect to critical values are interesting for two reasons. First of all, one should observe that when we have a line, the bars that can occur along that line can only happen between two projection of critical values onto those lines. These projections are usually called the push of the point onto the line. So for example, I could have a bar here because this is a push of this critical value and this is the push of this critical value. I couldn't have a bar here because this is not the push of anything. So first of all, the bars are only pushes of critical values. And also, if I have two equivalent lines, L and L prime, and I know that there is a bar here because maybe I have computed it, then I can immediately say that line L prime must have a bar here because of this. I can take this endpoint, I pull it back to the critical value, and then I push onto L prime. I take this endpoint, I pull back onto its critical value, and then I push it back, I push it back to L prime. And so I can compute this bar from this one without all the matrix reduction needed to compute a homology. And this is the reason why so this means that it is enough to compute the barcode for each representative line in each equivalence class, and then all the other barcodes for other lines can be computed in this way using pushes of endpoints of bars for the representative lines. Now, I want to use this also for computing the matching distance. So first of all, let me recall what it means that we compare two barcodes using the bottleneck distance. The bottleneck distance amounts to comparing bars of one barcode to the other barcode by a partial matching. Where I can, for example, match partial matching the sigma. I can, for example, match this long red bar to this long blue bar, and then I have a red bar that I can't match, so I leave it unmatched. When I've chosen a partial matching, what I can do is to measure how much I need to shrink or enlarge the two bars in order to make them coincide. And if they are matched, and if they are not matched, I want to I measure how much I need to shrink it in order to make it disappear. And then I take the values, the maximum among these values, X, Y, and Z, and I do this for all the matchings, and I take the infimum over all the possible matching sigma, and this gives me the bottleneck distance. So this is in order to compare two barcodes, but now we are in the fibered barcode situation where for each line I have a different barcode. And so I can decide that in order to compute the distance between two persistence module M and N, I simply fiber it along the lines, and I compare the barcodes I obtain along a line for the two modules using this bottleneck distance, and I adjust this distance, bottleneck distance, with the weight in order to obtain stability for this distance I'm defining, which is called the matching distance. And then I take the supremum over all the possible lines that are infinitely many. So again, the idea here is to use critical values in order to reduce this supremum over all positive lines with positive slope to finitely many lines, the least possible number of lines, in order not to waste too much time with computations. And so what we have is the following, that if we take, so if I have the critical values of the first persistence module M, the blue critical values, and the red point is a critical value for the second persistence module. And for example, I compute the barcodes along two lines in the same equivalence class, then I have troubles because, for example, when I push onto this line here, the blue barcode could be like this, and the red barcode, I should switch color, and of course it doesn't work, so I don't switch color. I hope you understand that the red bar could be like this. And so it is more convenient to match these two bars than matching this bar with the red one. But if I do the same on the line L prime, then the situation is completely different, because now when I push the blue points here, I get a bar like this. Where I push the point here, I get a bar like this. And if I push the red point, now I get this bar. And so it is more convenient to match these two bars, probably. And so we see that if I only consider two lines equivalent with respect to the points in C bar, there can be switches in the matching. So when I change a line with inside the same equivalence class. For this reason, we refine the equivalence classes, adding more points. So we add new points, which we call omega points, and the omega points depend on the critical values in a way that I will explain. And now the equivalence relation is fine enough so that there cannot happen no switchings between for matchings for lines in the same equivalence class. And so from this, we can show that the matching distance is determined only by these lines that are lines through 2 points in this extended set, a closure of C union omega, or lines through one of these points, but having diagonal direction. So this tells us that these lines are essential to compute. So we can reduce to these lines and not consider infinitely many lines to compute the matching distance. These omega points These omega points are well, it's simply combinatorial. We needed to consider many cases. For example, in the case where the points A, C from the critical values of M and B from the critical values of N satisfy this relation, we need to add a point omega with these coordinates because you can, and these are computations that you can derive quickly using Thales theorem, and so I'm not going into that. I just want to say that examining all the cases, you get all the coordinates of these omega points for all triples of critical points and quadruple of critical points. So in conclusion, if one wants to compute the matching distance using this method, one has to choose all possible triples of critical points and the quadruples of critical points to compute the omega points. And then one needs to consider all the possible lines through two of these points. And this gives maybe as bad as m to the 8 lines to consider, where m is the number of critical values of the persistence modules. And now one can compute the bottleneck distance along each line of this. And there is a new paper. I've not studied it, but I thought it was important to acknowledge that there is a new paper that seems to improve the cost of computing the bottleneck distance. And so what? Well, we get something whose computational cost is polynomial with a very high exponent, which is exactly the same exponent as the one obtained, I think, by Steve and Michael Kerber and Mike Lesnick in their paper. They use a different way of computing for the exact computation of the matching distance. But our hope is that by reducing the number of values to the critical values, this m can be small enough. So in conclusion, I've tried to give ideas on why I think that the critical cells, even in the multi-parameter setting, capture interesting aspects of persistence. And in particular, they can be used to determine the matching distance. But in this case, sorry, I forgot to mention, in this case, we have the result only for n equal 2, whereas all the rest was general for any n number of parameters. So now what we would like to do, of course, we would like to move from bipersistence to n-persistence modules. And also we would like to reduce the number of switch points so that the computational complexity may be decreases. And as I said, this is of course not work of myself alone, but with many collaborators. And this more recent stuff is with my colleagues Asilata, Robyn, Barbara, and Celia, for the last Women in Computational Topology workshop. And so I'd like to thank all of my collaborators and thank you very much for your attention.
Just to clarify one thing, how do you compare the critical values to the
the
multivariate numbers? Are these the same or?
Okay, I have studied this question with another collaborator, Andrea Guidolin, because today we also listened about the Morse inequalities for discrete theory, and we have a kind of Morse inequalities for persistence. But that involve these Betty tables of coming from the Koszul complex of multi-parameter persistence. We can't show that the two sets coincide. So the set of critical values, the closure of the set of critical values, and we know for, up to this point that the support of the Betty tables is contained in the closure of the critical sets. Critical values, sorry, in the closure of the critical values. But we don't know the converse inclusion. So, but we think they are related, but we don't.
Thanks for that. Very nice talk. Just a silly question. I thought from the relation to the matching distance for n persistence because
Yes, yes. This is we have not started yet,
Yes.
And the reason is because when we go in the three-dimensional space, it is not enough to add one point to block a line from passing from one equivalence class to the other equivalence class. But we hope so we'll study if we can. So I should say that the difference with the other method that is in the literature is that we are not using the point line duality. And the point line duality really, I think, unless I'm wrong, I could be wrong there, but I think that really needs that you work in the plane, because otherwise the duality is with a point and hyperplane and not with the line. So we hope that working with equivalence classes of lines, we just needed to figure out a way to substitute the omega points that block the switching to something else that blocks the switching, and we don't know what it is.
Okay, so let's thank Claudia again. Time for lunch.